And then part 6 is how big are the atoms, and I don't think that's very long either. So you figure on Friday, we're going to apply what we learned today. And then on Monday, we're going to talk about how big is an atom. And then Wednesday, I haven't decided. I might go ahead and start a little bit into Unit 3. But then the following Thursday, a week from tomorrow, you guys have your second unit exam for this class. Right before spring break. So we're bumping up against spring break.
Next Friday is our last day in the spring break.
Right. Yep. So that's all good. So today and Friday, we're going to be focusing on, where'd it go? On electrons. It's not in my title. We're going to be focusing on electrons. Oops, that's electrons. Okay, we love them. Okay, remember all the things we know about electrons? They're found outside the nucleus. And actually, according to the Schrodinger model, you can kind of think, the Bohr model said electrons are in different energy levels. We did all this, didn't we? And then the Schrodinger model said actually they are kind of spatially, you can use calculators to kind of see spatially where they are. We did all these, didn't we? Well, fast forward. Boop, boop, boop. Okay. So, electrons. Last week, we said that actually electrons end up in very quantized, that just means discrete, gotta be here, gotta be there, like they can't be anywhere in between. So we can kind of think of the energy levels where electrons are going to be as kind of on rungs of a ladder, okay? Just like that. So an electron orbital, oh, I think you must have this one too, right? Okay, electron orbital is kind of the region of space where the electron is. So we kind of think as the orbital is kind of its location, but it's also got a certain amount of energy on an energy, what we call energy diagram. So kind of location and energy. Okay. Okay, now this one's new, right? So actually I brought a diagram to kind of show you. We'll do this whole slide and then I'll kind of do a build and show you what I mean. Orbitals, though, to me, what you're going to see on the diagram here in a minute and next week, anytime you see a box, that is an orbital. That's a box when we're like finding homes for electrons. I say a box, but sometimes it's just a dash because I get lazy. Okay. The other thing, actually, I can tell you is that, and if you've had a chance to look at, I think this is chapter 9, chapter 6? If you've had a chance to look in your textbook about this, we use arrows to represent electrons. So that is an electron in an orbital, and this is an electron in an orbital. Now this last little bit already, where it says electrons in the same orbital, so you can, first off, it says you can put two, and I'm going to put a second one in these orbitals here in a minute. But if you have two electrons sharing the same orbital, they need to have what we call opposite spins. So to show opposite spins, what we do is we go ahead and draw an arrow pointing down. Okay, so I have two orbitals up there. They're maxed out at 2 electrons, and I've followed the rule that I need to. Actually, that's called the Paulis exclusion principle. Okay, coming up here in a minute. Paulis exclusion principle. Basically, they have to have opposite spins if they're in the same orbital. All right. Orbitals are grouped according to subshells. And I'll go ahead and give you kind of a precursor to what that looks like. There are different subshell types. There is an S-type subshell, and it has 1 orbital. And there's a P-type subshell, and it has 3 orbitals. And there is a D-type subshell, and it has, we got the whole oddsy things going on. So it's got 5 orbitals, and then we have an F. Guess what the pattern would be? How many orbitals does it have? 7, exactly. Let's see if I can fit 7 in here. Those are get to be ugly boxes. But these would be like different subshells, and they're kind of located at the same energy. And then last but not least, actually, you've already seen this, the n a minute ago when we saw the ladder. N is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4. Those are your principal energy levels. So it kind of like goes like, remember, energy goes up like that, and we have n is equal to 1. Oops. N is equal to 2, n is equal to 3. Those are our principal energy levels. So this is actually, I put this together last night to kind of sum it up. Let's see. Yeah, there it is. Okay. So I'll go ahead and push this out under Twitter in case you're interested. But here we go. Those are the principal energy levels. N is equal to 1, 2, 3, and 4, and we have energy going up. Now, on Friday, I'm going to go ahead and have to kind of undo what I'm going to tell you, especially here, n is equal to 3 and n is equal to 4, but that's okay. So down here we have an orbital, okay, and I have 2 electrons. All right. So when n is equal to 2, there actually are 2 possible subshells. Okay. I have an S-type subshell and a P-type subshell when n is equal to 2. Sometimes I call this the onion. Okay, so we're going up in energy. When n is equal to 3, guess what? It picks up 1 more subshell. When n is equal to 3, we have S, P, and D. So can you see that? We have 1 box, 3 boxes, and 5 boxes. And again, the green line is just kind of showing you the energy that those are at. And when n is equal to 4, actually, they can have 4 different subshells. And I kind of run into my title up here. One of my purple kind of runs in. But, so we have an S, P, D, and F. And usually at this point when I'm making my onion, kind of like that, I usually stop at n is equal to 4. We could go n is equal to 5, and actually there are 5 subshells. But it's kind of a long story. We're going to see that that 5th type of subshell, the G-type subshell, we never have to put electrons in there if that atom has electrons in their ground state. Okay, so then the last thing I did, okay, was to go ahead and add this little bit. So you can see the last thing I did was just to go back and for each one of those orbitals at the different principal energy levels, different subshells, I went ahead and put 2 electrons. And when I did that, I made sure they were pointing up and pointing down. It was fun. Okay. So those are actually a bunch of electrons. Okay. And like I said, on Friday, we'll start to kind of make sense of it. So we can already make sense of it a little bit. So if we were going to talk about, let's see, what would be a good one? Beryllium. Let's pick something simple. Beryllium. It's atomic number 4, so it has 4 protons in its nucleus. So if it's neutral, it has 4 electrons. Okay? So actually, I could go ahead and draw a circle around these 2 orbitals, and that actually is how those 4 beryllium electrons are hanging out. That's how they're, what we say, configured. Electrons try to find the lowest energy, and they build up when they run out of room. So again, we'll be talking more about that on Friday. Okay. So I like kind of showing you that, so we're all kind of on the same page with this. So if you take a subshell and you have multiple orbitals at that same principal energy level in that same subshell, like 2p, you have those 3 orbitals. Those 3 orbitals for 2p, those 3 orbitals in the 2p subshell are all what we call degenerate. Okay, and degenerate just means that they share the same energy. Okay, so that's kind of nice. And like I kind of showed you, subshells are, let's see, subshells of orbitals. Okay. So notice that though on the diagram that I kind of showed you a minute ago, when it came to the P type, we had 2p, and then we also had 3p. Okay, now those 6 would not be degenerate. The 3 and the 3 orbitals in the 2p would be degenerate, and the 3 orbitals in the 3p would be degenerate. So I think you're probably good with that. So here's a figure from your textbook that kind of talks about, now it's not like onion like I did before, but it does do like what I did. It goes up to n is equal to 4, and it goes, here is your, this is your 1s, and then we have 2s, 2p, 3s, 3p, 3d. You'll be talking about this in your sleep. 4s, 4p, 4d, and 4f. And already, though, what I don't like is that, for instance, all these p's, just like you saw in my onion diagram, all of these p's actually have 3 boxes or 3 orbitals. And all of these d's have 5, both those d's. And this f has, of course, 7. Okay? So I like my onion better. This is just another way to look at it. This is if you're kind of doing energy, energy would kind of go the lowest energy at the top, and increasing energy should go down. Principal energy levels. I told you that actually we kind of stop at n is equal to 4. Okay, but when n is equal to 5, it actually picks up a 5th subshell. When n is equal to 6, it picks up 2 more subshells. Okay. So those are actually there, but like I said, on Friday I'm going to try to convince you that we never have to occupy those ones in parentheses. Picking up with the pattern, so it would have, the G-type would have what, 9? The H-type would have 11. Okay, we have lucky number 13 with the I-type. As far as orbitals go. Okay. So I keep talking about Friday. I'm kind of anxious to get to Friday. I thought about starting in on part 5, or the next part, but I thought, no, we'll just wait till Friday. But when we start to kind of what we say find homes for electrons, I'll pick on beryllium. Okay. Actually, beryllium, I already kind of told you, it's atomic number 4. Okay, so a beryllium atom, you have to find homes for 4 electrons, assuming it's neutral. A minute ago, I said, all right, so actually it's going to look like this. There are 2 electrons here, and there are 2 electrons here. Oops, sometimes oops. Okay, so those are the 4 electrons around a beryllium atom. Now, according to this slide, if you were to find the highest n, so I'm hoping you guys are kind of catching on that the n is the number. Okay, so here we have n is equal to 1, here we have n is equal to 2. Okay, so actually, in terms of valence electrons, those are beryllium's valence electrons. Beryllium has 2 valence electrons. Where are they located, and what energy do they have? They're both in the 2s subshell. 2 valence electrons. All right. So, I feel like we've kind of already been talking about this. The whole S, P, D, and F. S is 1 subshell, or excuse me, S is 1 orbital, P subshell is 3 orbitals, a D subshell is 5, and F subshell is 7. You know, when it says according to quantum theory, see, this is where, and there are definitely places where chemistry and physics intersect. Okay, so quantum theory has a lot of interesting outcomes. One of them, what I remember, is you should be able to walk through walls. The matter of you should be able to walk through the matter of the wall. That's quantum theory. But usually it's a small scale, kind of like electrons. So, yeah, there's that. So, and this is kind of goes back to the diagram, like I said, I'm going to push out on Twitter, this idea of, you know, if you bump up to n is equal to 3, when n is equal to 3, do you remember we had 3 subshells? So we had 3s, 3p, and 3d. That's kind of how it goes. N is equal to 4, we have 4s, 4p, 4d, and 4f. And kind of as I put my hand up, that's more energy. All right. So an orbital is both energy and location. Not only is it location, but the different types of orbitals, the S, the P, the D, and the F, they have different shapes. And so actually, I'm so excited because when I talk about the shape, I'm literally talking about how are the electrons distributed? What is that little fuzzy thing we call the electron cloud? What does it look like? Okay. So S, we're going to look at some pictures here in a minute, but any S type, whether it's a 1S, 2S, 3S, 4S, 5S, you know, any S type subshell is going to be spherical. Any P type subshell is going to be dumbbell shaped with actually, for the P type, I'll go ahead and kind of show you what this picture looks like. So for the spherical ones, okay, this is the nucleus, and of course we kind of have that's S, okay. For P type, this again is the nucleus, and when they say dumbbell, they basically mean, okay, so it's kind of lobes out on either side of the nucleus. So both of those lobes make one P orbital. And so it's kind of cool. If you look at this one right here, the probability for the P type, the probability of finding an electron right where the nucleus is, where that red is 0. I think that is so cool. So the spherical and dumbbell shape S and P are the easiest to kind of visualize. So we'll kind of take a look at those. So this would be an S type subshell, and that the thing kind of makes you itch. Those are kind of, that's the cloud where that pair of electrons, well, it could be just one electron occupying it, 1 or 2, but it maxes out at 2. Electrons can be found. This actually is a 1S orbital. And what we're going to see is not only is 1S the lowest energy, okay, but it's also closest to the nucleus. Okay, so if we scale this up here in a minute, showing you kind of a 2S, 3S, etc. I don't have the videos, they didn't work for me. So I guess this is the only one I can show you next. So here we have the 1S at a lower energy closer to the nucleus and a 2S higher energy further from the nucleus. Higher energy. Now, are we going to have to go ahead and put electrons? Are electrons going to have to, what we say, occupy our 2S subshell, a higher energy? Yeah. We saw that with beryllium. Beryllium had 2 electrons in the 1S, 2 electrons in the 2S. So this must be the P type. It's dumbbell shaped. Again, kind of in the center of those lobes is the nucleus, the center with the center of the atom with the protons and neutrons. And we said that any P-type subshell has 3 orbitals. It's kind of fun because that's one orbital, okay? And that's another orbital, and that's the 3rd orbital. So it's kind of fun spatially. We kind of have them, if you think of X, Y, Z coordinates, we kind of have a pair of lobes along the X, plus and minus. We have a pair of lobes along the Y, plus and minus. We have a pair of lobes along the Z, plus and minus. Okay, I don't know what we'd do if we had a 4th orbital, where we'd put that. But I just think that's so cool. Electrons totally rock. So if I were to ask you, and again we'll get to this a little bit on Friday, let's just take let's just take 2p. Let's see, 2p. A little bit ago for my onion, since it's a p type, of course we have 3 subshells. Sorry, 3 orbitals in that one subshell. I have 3 orbitals because it's p, and we can put 2 electrons. And usually when I go ahead and show my pair of electrons, I usually am lazy and just kind of show a half of an arrow. Okay, but I bet you guys are okay with that. I hope you are. Okay, so those are what, 6 electrons? We kind of max out with 6 electrons here in any p-type subshell. But my point is going to be that I think this is so cool. This is actually 6 electrons, or it has the potential to be 6 electrons. Okay, so here we see our P sub X, our P sub Y, and our P sub Z. Okay. Again, kind of at the center there is the nucleus. So now when you go up to D's, they look weirder. So S's are spherical, P's are dumbbell shaped. D's are a little bit weirder, and F's are weirder yet. So here's the D. Now the D, we need to actually spatially be able to have clouds that accommodate 5 because it's a D type. And so there's one. Isn't that cool? I just think that's so cool. Okay. There's 2. Literally, that's the spatially where the electron, a pair up to 2 electrons are buzzing. There's 3, 4, and 5. I love the 5 one. Like, really? Are you serious? You know, I just think that is so cool. And shape and energy, obviously, of the subshells have consequences. Okay, so just to kind of summarize, these are all S's. Okay, notice that they're getting farther from the nucleus. We have 1s, 2s, 3s. Here's our P's, 2p and 3p. And there's our D. And this is with regard to F. This is just one of how you would show the region space where up to 2 electrons could reside. One of the 7 F orbitals. Pretty cool. Okay. So I mentioned this before, the Paulis exclusion principle. There's actually, this is a principle, and then there's actually a rule that we're going to cover on Friday. So Paulis exclusion principle is the reason, and I can go ahead and kind of sum it up here as a picture. If I were to draw an orbital in the box, okay, and I were to do one arrow up, you would tell me the next arrow needs to go down. To me, that is the Paulis exclusion principle. It basically says, all right, that's fine. You can have 2 electrons. You can have 2 electrons in one orbital, but if you do, then one has to actually have, they have to have what we call opposite spins. And we aren't going to talk about it. We talk about it in General Chemistry 1. We're not going to talk about it in Intro to Gen Chem, but actually we would call this has what we call an M sub S value, a value of +1/2, and this guy going down has an M sub S value of -1/2. That's kind of what we do with that. But opposite spins will work for you. And actually, I can see in my slide now, you know, we don't really, yeah, I think that'll do it. Okay. So again, just to kind of recap, if you were to go ahead and completely fill a subshell, S's have 1 orbital. You can put 2 electrons in that 1 orbital, so you max out at 2 electrons. So this is actually going to help you on Friday. So any S, it's a 1s, 2s, 3s, you're going to max out at 2 electrons if you fill that subshell. Any P, okay, you have 3 orbitals. You can put 2 electrons in each, so you're going to max out at 6 electrons in any P-type subshell. D-type, you have 5 orbitals. You can shove 2 electrons in each, so you max out at 10. And an F-type, you have 7 orbitals. 7 times 2 is 14, so you max out at 14 electrons. So on Friday, when we start to actually find out how electrons are hanging out, how they're configured, we need to kind of remember this. Okay, so we'll take a quick look at these. Again, this is in Chapter 9. We are clear up in Chapter 9 now. Kind of bouncing around a little bit. But I think my lecture notes actually have I think my lecture notes have what's called a lecture guide at the beginning of the unit to tell you kind of the roadmap for where we'll be going in a chapter or in a unit. So 19 looks like this. List 4 possible subshells. The number of orbitals in each subshell and the maximum number of electrons that can be contained in each subshell. So I bet you're okay with this. We're looking for basically S, P, D, and F, that sort of thing. For the next one, Sketch the 1s and 2p orbitals. How do the 2s and 3p orbitals differ from their counterparts down an energy level? So this is where you're going to draw the s's as spherical, right? And you're going to draw the p's as dumbbell shape. Okay. And remember we said that when you go up to the higher energy, like the 2 and 3 versus the 1 and 2, they're going to be further from the nucleus. So that's kind of what their sketches look like. 45, which electron is on average closer to the nucleus? They're both in s's, but we have a 2s and a 3s. I'd say 2s. I want to do your homework for you, but I think you'll do fine. 44, just do your best at sketching the 3D orbitals. Okay, just do your best. And then how would they compare with a higher energy level instead of 3, 4? And 46, yeah, which electron is farther from the nucleus? That'd be the higher energy, because they're both P, right? 3P. All right. So actually, that's about as far as I wanted to get today. Like I said, a little shorter. And come tomorrow, we'll be using Bunsen burners flame, so just think safety tomorrow.